So welcome back. We're going to be looking again at how to fit copulas in this session, and we're going to be looking at how to do that for elliptical copulas. So we're going to start with normal copulas, which are the most straightforward type of elliptical copula. Now, if you remember what we did before, the first thing we did was we created a copula object, and this time I'm going to create one in 6 dimensions. And doing this for normal copulas, we need to add an additional parameter which is relating to the dispersion structure. And the reason we need to set this is we need to set it to unstructured, UN, and this means that every pair of variables has a separate correlation coefficient. If we don't have an unstructured dispersion structure, then you'd have a single correlation coefficient being imposed across the whole dataset, which you don't want with a normal copula, because part of the point of using a normal copula is you can have a whole range of correlation coefficients. So to do this, we create normal object. If you remember from last time, I told you that naming these things isn't my strong point, so normal object is your normal copula object. And this uses the function normal copula, dim equals 6, so 6 dimensions, and dispstr equals un for the unstructured dispersion structure. We then just use fitted normal ml as the name of our data frame, or the name of our results, and into this we put fit copula, which is the command we use, and inside that normal object, which tells us it's that normal copula object we just created as the framework that we're going to use, ret sum u, which if you'll remember is the data that we created, they are uniform distributions, and we don't need to specify the columns here because we're using all 6 columns. And then again, method equals ml, that means we're using the maximum likelihood method. And again, showing the results as fitted normal ml. So this is what the code looks like in the top left, and then on the bottom right, here are the results. So the first thing you can see is we've got a lot of rows listed out there, which isn't particularly helpful. And we've also got the log likelihood from the fitting process, which will come in useful a little bit later. So, as I mentioned last time, additional information is available using the summary command. And also something which can be useful is some details on what the various slots, as they're called, are, so that we can call them. If you use this slot names function, what it does is it tells you the names of the different components within the object that you've created, so you can call them individually. So, if we look at the summary, that gives us a list of all the correlations, and also gives us the standard error on those correlations as well, which is quite nice. And you've got the maximum likelihood there, and it also tells you how many iterations it took to get that maximum likelihood. And then below you can see the slot names are listed: copula, estimate, log likelihood, method, fitting statistics, and so on. So what this means is if we wanted to get any one of these, we could just pull that data out rather than just having to look at the whole picture of the summarized data. And this can be useful if we want to actually do something with a particular item from that data. So one thing which you can see which isn't particularly helpful is this vector of correlations. Now, it's fine as it is if you're going to be using this copula as it is to then create more simulations or to derive probabilities. You don't need to do anything with it. But if you actually want to look at these correlations and say if these look useful or not, well, you can coerce them into a matrix for later use. So you can actually create a correlation matrix which you can then investigate and see how those numbers look, whether you'd want to change anything about the data that you are modeling. So to do this, the first thing we do is we create a 6x6 matrix. And you remember before when we created that empirical distribution, the way I did it was I used an existing data frame to create the framework for the new one. If you haven't already got a matrix, then you actually need to create it. So the way that I do that is I create a name for my matrix, for my normal correlation matrix, which is normal core matrix, and I say that is a matrix which contains just zeros, so that's what the 0 is there for, with 6 rows, so n row equals 6, and 6 columns, n col equals 6. And what that will give me is a 6 by 6 matrix which just has zeros everywhere. Then I put into that all of the data using this information. So what I do is I say, if the column of this matrix is less than the row of the matrix, then stick some data into it. Otherwise don't. And what it will do is it will go through all of the cells for which that is true in order, and it will drop in the data from the next part. Now the next part is fitted normal ML at estimate. What this is, estimate is that list of correlations, and the at before it tells you which bit of fitted normal ML you're going to get. So you remember those slot names that we dug out? One of those was estimate, and to pull that information out of the object fitted normal ML, we just type in fitted normal ML, then at and estimate. That'll give us just the correlations. What we then do is something quite clever. We take normal core matrix and we transpose it. So if you transpose a matrix, your rows become columns, your columns become rows. You essentially flip it along the diagonal. Because what we've created there is just a triangular matrix. And we create a triangular matrix based on the columns number being less than the row number. So if the column number is greater than the row number, you've still got zeros in there. So what we've created is a lower triangular matrix. If we transpose it, we've got an upper triangular matrix. And what we can then do is, if we transpose it and add it back to itself, we've added a lower triangular matrix to an upper triangular matrix, we've got a complete correlation matrix. And then the only other thing we need to do is to say, well, what's happening with the diagonals? Well, the diagonals of a correlation matrix are always going to be 1, because the correlation of any variable with itself is 1. And then if we type out normal core matrix, we will see this beautiful, symmetrical, complete correlation matrix. So that's the code at the top left, and in the bottom right you can see what you've got is a correlation matrix. So all that vector of correlations is being coerced into a nice, attractive looking symmetrical correlation matrix. Okay, so that was normal copulas. What about T copulas? You've got a very similar process for T and normal copulas. I mean, they're both elliptical copulas, but clearly with a T copula, the additional component is the degrees of freedom. And you can either fix this or you can find it by optimization. So the way that you deal with that is by using the df.fixed parameter, and I've set it to false. What that means is it's going to try and find what the best degrees of freedom is, what the optimized degrees of freedom is for this copula. Now again, the first thing we do is create this object, which I've called a T object. And we do this using T copula, and we say it has 6 dimensions, so we're using all the data again. Again, an unstructured dispersion structure, and as I said before, df.fix equals false. We then come up with our object, fitted TML, which we dump the results of this optimization in using the command fit copula. And what kind of copula are we going to fit? Well, it's a T copula because the framework we're using is defined by T object. The data again is coming from ret sum u, and again we're using the maximum likelihood method. And then we display the results in fitted TML. So the code again on the top left, this is how it looks, and then the results at the bottom. And you'll see the results look very similar. We've just got one more item there, which is df 6.2132, that's the degrees of freedom. So it's not quite the same, but it's very similar. And again, we've got the log likelihood there and the optimization converged. Well, that's good to know. So you note that the results include the log likelihoods. And this means that we can compare the models using, for instance, the Akaike information criterion, the AIC, or the Bayesian information criterion, the BIC. So the AIC is 2n minus 2 log L. So n is the number of variables that you've got. And the Bayesian information criterion is n log t minus 2 log L. So t is the number of observations, multiplied, logged and then multiplied by the number of variables. So for both of these, a lower number is better. So And that's because you're subtracting the log likelihood, and the better fit a model has, the higher the log likelihood, so you get a lower number for a better fit in the AIC or the BIC. And what you're penalised on is having more variables. So the higher n is, the more variables you've got, the worse your AIC or BIC will be. And then the Bayesian information criterion has a much higher penalty for additional variables because you're multiplying it by the log of the number of observations. So if you've got a lot of observations in particular, the BIC is a much tougher criterion, much higher penalty for adding additional variables. And the additional variables you've got here, if you're comparing a normal distribution and a t-distribution, is that additional parameter for the degrees of freedom. So what you can do with this is you can say, well, I'm adding an extra parameter in terms of degrees of freedom. I'm allowing it to adapt the shape of the data more. But is it worth it? Is my fit so much better that the penalty I incur by having this additional variable makes it worthwhile? So you can do this by just running the command AIC or BIC on those copular objects, fitted normal ML, fitted TML. So you don't even need to explicitly use the log likelihood because those functions will see there's a log likelihood function in there and then use it to calculate these items, the AIC and the BIC. So that's how the code looks, and there's the results. So for the AIC for the normal and the T, and the BIC for the normal and the T, you can see that for both of them the T copula is a better fit to the data than a normal copula, which is kind of what you'd expect, I think, when you've only got 6 degrees of freedom. That suggests you've got fairly non-normal joint tails in that copula. And it shows that using a T copula rather than a normal copula for this data is a significantly better fit. The penalty that you incur from having that extra variable, the degrees of freedom, is more than offset by the improvement in the fit that you have. So that's everything on how to fit copulas. What we're going to do next time is look at how to actually evaluate copulas and even how to simulate them, because both of these are pretty straightforward, so it won't take very much time to cover, and I should be able to hopefully cover them both in the same short video. But hopefully that's been useful. You can see that for things like normal and T copulas, you can very quickly get some useful information on not just how you fit them, but how good the fit is with very little work indeed. So thanks for tuning in, and I shall see you next time when we do a little bit more on copulas.